So let me start this talk. Thank you, Chairman. So this is acknowledgement. The author would like to thank organizers of this workshop, Dr. Khan, Dr. Imaizumi, and Dr. Sunyama. Thank you. So this is the contents of my presentation. First, I talk about unknown uncertainty. And so singular learning theory is introduced. And last, deep learning and AI alignment will be discussed. So let me now go on to my first point, unknown uncertainty. Why unknown uncertainty is necessary? In the Bayesian statistics in the 20th century, it was assumed that a person or AI could believe that a world is small and uncertainty could be captured by a personal belief. However, if statistical inference is defined on a set with infinite elements, then the dimension of the set of probability distributions is infinite, resulting that a person and an AI believe that uncertainty is different from any specific model. This is sometimes referred to as, so all models are wrong. I think you know this words. We need mathematical framework for a person and an AI, artificial intelligence, in the case when a model is different from unknown uncertainty. So this is a case one, personal framework of unknown uncertainty. Assume that a person or an artificial intelligence believes both unknown uncertainty and personal or AI belief. So here Q is taken from functional probability distribution large Q, and then Xn is independent random variables taken from Q, small q. Here, this is a statistical model. Parameter theta is subject to some prior distribution pi, and then Xn is taken from this statistical model P of Xi for given theta. This is unknown uncertainty, and this is a personal or AI's belief. This is case one. So this is case two. This is a scientific framework of unknown uncertainty. A scientific assumption is set as this. Here, this is an unknown data generating process. This is the same, mathematically, this is the same as the previous one. A scientist prepares a candidate model. This is a candidate scientific model. Here, this is a prior pi. And so this is a statistical model P of Xi for given theta. In existence of an unknown uncertainty, in both cases, the same mathematical theory holds. And moreover, the pair pi and p is contained in some unknown functional probability distribution Q and the probability distribution small q. If a person or an artificial intelligence believes some pair pi and p, then they automatically believe the existence of unknown uncertainty Q and Q. If a person or an AI believes the existence of some pi p and known existence of Q and Q, general Q and Q, then they believe a mathematical contradiction. So if Xn is subject to unknown uncertainty, a functional probability distribution large Q and the probability distribution Q, then it is exchangeable. The central limit term holds for each Q, which is generated from Q. For example, sample mean, this is sample mean, convergence of the expectation of X for given Q. Note that this limit value is not the expectation of X, but this is this convergence, this random variable convergence to the expectation of X of Q for given small q. So this is a definition of the posterior distribution. For a given candidate pair P, a statistical model, and a prior pi, the posterior distribution is automatically defined by this equation. Here, this is a probability distribution of theta for given xm. So that this is a prior, and this is likelihood function, and this is a normalizing constant. Here, normalizing constant P of xi is the marginal likelihood. This is the expectation of pi and likelihood, and so this is integration over the parameter. The expectation value by the posterior distribution is denoted by E theta for given xn. So this is a definition of the predictive distribution. The posterior predictive distribution is defined by the expectation of the statistical model using the posterior distribution. And this is denoted by P of x for given xn. But this is different from unknown uncertainty Qx. So we would like to know that the difference between the unknown uncertainty Q and the estimated posterior predictive distribution P of x for given xm. So, here, generalization loss and the minus log marginal likelihood is defined. Here, generalization loss is defined by of E of x for this is a predictive distribution, and so minus log predictive distribution. This is the expectation by using unknown Q. This is a generalization loss. The minus log marginal likelihood is sometimes called free energy. Free energy is defined by this equation. Fn is equal to minus log. This is marginal likelihood, P of xm. So then the generalization performance can be measured by these equations. Here, SQ is the entropy of unknown uncertainty Q, and Xn is defined by direct product of Q of Xi from I is equal to 1 to M. Then these equations hold. These equations hold. E of Fn is equal to N times entropy, and Kalbach-Leibler divergence from Q of Xn to P of Xn. So the expectation of Gn for given Q is equal to the entropy and Kalbach-Leibler divergence from Q to predictive distribution. This is predictive distribution, and this is marginal likelihood. So here, the expectation of Gn is equal to the increase of the free energy. Here, this is Fn plus 1, and this is Fm. Thus, there are mathematical relations between the generalization loss and the free energy. This equality holds for not only E of expectation using for each Q, but also the expectation of all over Q. So this is a leave-one-out cross-validation, LOOCV. Here, leave-one-out cross-validation is defined by the empirical sum of log P of Xi. Here, the Xn, this is set minus, this is a sample, and Xi is so the Xi is left out. So this is a leave-out cross-validation, and then it follows that the expectation of Gn minus 1 for each Q is equal to expectation of Gn for each Q, and thus this is the expectation of Gn minus 1 is equal to expectation of cross-validation loss. Now let me now go on to the second point, singular learning theory. So here, why singular learning theory is necessary? If a map from statistical model P of X for given theta is not 1 to 1, and if the posterior distribution could not be approximated by any normal distribution, such a model is called singular. Singular models are ubiquitous in machine learning. For example, deep learning, normal mixtures, topic models, matrix and tensor decompositions, and almost all learning machines are singular learning machines. Here, this is the definition of two log loss functions. So L theta is the expectation of minus log P. This is a statistical model for each Q. And Ln theta is the empirical sum of log P of Xi theta. Both theta 0 and K theta are defined by this equation. Here, theta 0 is one of the argument of the minimization of L theta, and K theta is equal to L theta minus L theta 0. In general, L theta is not unique, but L theta is, in general, it is algebraic variety. So here, this is a classical regular case. This figure shows the horizontal surface is a parameter, and so the longitudinal line shows K theta. In the classical regular case, K theta can be approximated by a quadratic form. However, in neural networks, normal mixtures these are singular models, and k theta has this form. In this case, a statistical model is called singular. In order to study these singular models, we need Hironaka theorem. This is a well-known theorem in algebraic geometry called resolution of singularities. Yeah, you can find a parameter set, and so k theta. This is we assume that k theta is analytic. So for an arbitrary analytic function k theta, there exists some analytic manifold, and analytic function theta is equal to gu, and so, such that kgus is equal to normal crossing function u1 to k1, u2 to k2, and ud to kd. And this is a Jacobian determinant, and this is equal to a positive function pu, and u1 h1, u2 h2, and ud hd. Thus, by using this theorem, a statistical model can be understood as defined on this manifold, and it has only normal crossing singularities. So in this case, but on the manifold, there are many local coordinates. In each local coordinate, k1, k2, kd, and h1, h2, hd are determined, but these are which defined on local coordinate. So here, in this local coordinate, this is normal crossing singularity, and in another local coordinate, this is is given by normal crossing. However, they are different in general. So this is the definition of real log canonical threshold. This concept is well known by rational invariant in algebraic geometry. The real log canonical threshold and its multiplicity are defined by this equation. Here, RLCT lambda is equal to minimization of the local coordinate and the minimization of hj plus 1 over 2kj, and multiplicity is equal to the maximum local maximum value of the local coordinate of the number of the set j's such that lambda is equal to hj plus 1 over 2kj. This is so this sharp means number of the element of this set. Note that if kj is equal to 0, then this is defined as infinity. So this is the main results of singular learning theory. Let lambda and m be a real log canonical threshold and its multiplicity. Then Fn, the free energy, this is equal to the minus log marginal likelihood is equal to n times ln theta 0 plus lambda log n minus n minus 1 log n, and constant order term. Gn is equal to L theta 0 plus lambda over n plus lambda n over n. Here, lambda n is a random variable whose expectation is equal to 0, and lambda n converges to some random variable lambda in this distribution. And this is smaller order term. Cross validation loss is given by this equation. But remark that this sign and this sign is different. Thus, the expectation of Gn is equal to the expectation of the cross validation loss asymptotically, but they has so inverse correlation. This remark, inverse correlation of the generalization loss and cross validation. Notation Gn minus L theta 0. This is generalization error. And Cn minus ln theta 0. This is called cross validation error. Remarks that generalization error has the inverse correlation with cross validation error. Gn minus L theta 0 plus Cn minus ln theta 0 is equal to the constant and smaller order term. This equation may cause incorrect evaluation. So if you use revert cross validation to estimate the generalization error, then you had remarked this inverse correlation. So let me now go on to the last point: deep learning and AI alignment. Unknown uncertainty and deep learning. Machine learning can be understood as statistical estimation of unknown uncertainty by a probabilistic model. Here are input x and output y. So here this is unknown uncertainty. And this is a neural network or deep learning. Here, x and fx theta plus so some random noise. This is learning. Nowadays, artificial intelligence alignment is said to be necessary. Artificial intelligence alignment is sometimes defined as AI working without deviating from the designer's intention. In order to consider artificial intelligence alignment, we need all studies of all different points of view. In this presentation, the presenter would study artificial intelligence alignment from a mathematical point of view. Singular learning theory and AI alignment. Recently, research on singular learning theory and artificial intelligence alignment is becoming more active. For example, Dr. Wei and Marfet studies that deep learning is singular, and that's good. As they said, deep learning has singularities, but it is good property, they say. So Professor Yang showed the generalization loss of the deep linear neural network. And so Dr. Nagayas shows that a generalization performance of deep ReLU network with skip connection. He proves that ReLU network has the different generalization performance if it has skip connection or if it does not have skip connection. So Dr. Hayashi and Dr. Sawada showed a partial concept bottleneck model they studied PCBM by using singular learning theory. So let me study Fisher information matrix. The matrix I theta is called Fisher information matrix. Here, I theta is the expectation of x. This is the partial derivative by theta, fx theta, and partial derivative of fx theta. Here, fx theta is equal to log p of x for given theta. This is a Fisher information matrix. I think you know this matrix very well. This figure shows the horizontal line shows the eigenvectors in ascending order, and the longitudinal line shows eigenvalues. In deep learning, almost all eigenvalues of Fisher information matrix are 0. These eigenvalues of Fisher information matrix is equal to 0, and these are not 0, but these eigenvectors are very small part of all eigenvectors. In classical models, Bayesian posterior convergence. So if Fisher information matrix is positive definite, in otherwise, all eigenvalues are positive, then the posterior distribution concentrates on the best parameter as n tends to infinity. Here, this is a posterior distribution for n is equal to 10, and n is equal to 100, and n is equal to 1000. So posterior distribution converges. The posterior distribution seems to represent a gradual increase of learner's confidence. So this is a classical model. Deep learning have many singularities in parameter space. This is deep learning, and this is a parameter set. This is parameter set, and this parameter corresponds to some largest model, and this parameter corresponds to a medium model, and this parameter corresponds to a smallest model. If a statistical model is redundant, then the posterior distribution does not converge to one point, but it is near the algebraic varieties. This figure shows the learning process. Learning process in the phase transition. Here, this is n is equal to 10, 10, and so n is equal to 10, 100, and this is equal to n infinity. In modern learning machines, the posterior distribution jumps from a singularity to another singularity. Even if the sample size is huge, it is far smaller than the infinity. Such jumping process makes it difficult to diagnose whether the learning process is out of order or not. Here, if n is small, then this is a posterior distribution. You can find you can find the posterior distribution near this singularity. As n increases, it jumps from here to here. The posterior distribution, you can find this posterior distribution near the singularities in another singularities. And if n is equal to infinity, this may concentrate on this, but this in a real world problem, n does not infinity in general. This figure shows the phase transition. The horizontal line shows the sample size m, and the longitudinal line shows free energy. Here, this is a free energy of the smallest model, and this is a free energy of the medium model, and this is a free energy of the largest model. Here, in this case, phase transition occurs. Here, the smallest model, the posterior distribution changed from the smallest model to a medium model. And here, the posterior distribution changes from the medium model to the largest model. In this case, this is phase 1, and this is phase 2, and this is phase 3. So this remarks that the free energy is different from generalization error. The local coordinate chosen by the posterior distribution makes free energy smallest. This is the definition. This is by the definition of the posterior distribution. But the base singularity for the minimum generalization error is different from the minimum free energy. Here, the horizontal line shows the sample size, and the longitudinal signs the generalization error. This is a learning curve over smaller model, and this is a learning curve of a larger model. Then Gn, the learning curve of the Gn is given by this line. Here, you can find this phase transition. The posterior distribution changes the smallest to the medium size, but this becomes generalization error larger. This figure shows the learning curve of deep learning. Here, horizontal line shows sample size, and the longitudinal line shows the generalization error. So the learning curve is given by this equation. These are learning curve of each local coordinates, each singularities. And so the learning curve is given by this red line. In deep learning, the posterior distribution jump from singularity to another singularity. The jump is optimal for the minimum free energy, but it is not optimal for the minimum generalization error. Alignment problem caused by singularity. In modern learning machine, the learning process as the increase of the sample size jumping from a singularity to another singularity. Even if the sample size is huge, it is far smaller than the infinity. Deep learning always remains in singular state. It is difficult to diagnose whether the learning process is out of order or not. A mathematical challenge is to make a method how to distinguish the proper jumping process from the state out of designer's intention. So this is a mathematical problem for the artificial intelligence alignment. Conclusion. First, a method how to formulate unknown uncertainty is necessary in modern statistics and machine learning. Second, singular learning theory is a mathematical framework which enables us to study deep learning. And last, singular learning theory will play an important role in AI alignment. Thank you.
Okay, so we are open for discussion and questions or comments.
Thank you very much for the great talk. So in the first part, you talk about cross-validation. Can you go back to the correlation? Right. So there's inverse correlation. So this means just using the cross-validation score for like model selection is not appropriate.
It may be. This is this equality holds in base estimation, but in the maximum likelihood or the maximum a posteriori estimate, the same equation holds. It is not so difficult to show this inverse correlation.
But in practice, still many people are using some kind of validation score for model optimization.
So in general, a model evaluation depends on the bias and variance. This inverse correlation occurs if the variance, if the bias is equal to two models. In general, both should be considered.
So as long as we compare two models with the same bias, then cross-validation is still fine?
In that case, if you use cross-validation, then you mischoice. So
the other way,
if cross-validation is small, then generalization loss becomes large.
If two models have the same bias.
Same bias.
I see. Thank you very much. Maybe somebody want to ask another question.
Thank you for your great talk. So I'm interested in like a jump among different singularities, and maybe so that's my question. So there are two types of singularity from the red and blue. So is there any specific characterization of these singularities? So the blue has a more larger intrinsic dimension also. So is there any difference about the blue?
Sorry, please explain much more.
Sorry. So is there any specific characterization, difference of the characterization of the red singularities, the blue singularities? So
here this is singularity and this is another singularity.
So
these corresponds to another local coordinate.
Yes.
So another model.
Yes. And
the posterior distribution near here goes to near here.
Okay. Yeah, thank you. And I guess that the some singularity can have a larger kind of intrinsic dimension also. So is there any kind of specific, the difference, the blue singularity should have a larger dimension or a smaller dimension, the kind of the.
So this singularity corresponds to the small model, and so it has a smaller real log canonical threshold, and this model corresponds to the larger model. And in this case, the real log canonical threshold is large.
Okay. Thank you very much.
Okay.
Yes.
Yeah, thank you very much.
More questions or comments? If no, yes.
So for the negative correlation between the generalization error and convergence error.
For the negative correlation between generalization error and the cross-validation error, can your result be applied for not a cross-validation but a holdout validation? Because currently in machine learning we don't really use cross-validation. We split some data from training data or test data, and those validation data never draw training.
So here, this cross validation is leave-one out cross validation. This CN is leave-one out cross validation.
We repeat in time. People now. So nowadays we don't really repeat validation process anymore. Not only once.
Only once.
We have the same phenomenon for validation process only once.
So only once, or given for some sample set, or given for a sample for XN. Hold out, you said hold out cross validation. Hold out cross validation has another probabilistic property. Holdout cross validation. Holdout cross validation does not satisfy this equation. But I think holdout cross validation is not so precise as the leave out cross validation. If you want to know the generalization loss, the leave out cross validation may be the better estimator than the holdout cross validation. Thank you.
More questions?
Yeah, and I have a tiny question. So you mainly consider the uncertainty from data, but I'm just wondering that is it possible to incorporate the uncertainty from algorithms for deep learning? So because the mini training algorithm in deep learning is very random, so it's also another source of the randomness for deep learning. So is it possible to incorporate this?
Do you mean some arrangement dynamics? So I think you know the arrangement dynamics convergence to the base posterior distribution in general. But in general, it does not converge in the small learning times. So the generalization error by the arrangement dynamics is very important. But I think it is not known. It should be studied. Okay.
Thank you.
Thank
so
you.
If no other questions, we thank our speaker again.
Thank you very much.
Thank you very much. Thanks very much for having me. Very sorry to be remotely, but great to join this excellent session. Okay, so this is part of a project that we have been running on combinatorial and implicit views on deep learning. Combinatorial in the sense of the structures that may arise in the parameter space in relation to a data, and implicit in the sense of the functions that we are representing with neural networks. But today I'm focusing on the combinatorial aspect and what it can tell us about the optimization problem with ReLU networks that have a mild overparameterization. Talking specifically about a work that we did recently with PhD student Carr and postdoc Michael Murray and a former PhD student Hannah Saran, who is now in Tokyo, as a matter of fact. All right, so here's the overview. So we know that neural networks have a non-convex loss landscape, which may have many local minima and plateaus. And we have this question as to why bad local minima do not seem to be a problem for training our networks. And one of the observations that has become kind of prominent is that if we have an overparameterized network, then the optimization problem gets easier. And not only that, but also we may hope to get a better generalization properties for the solutions that we find in those overparameterized networks. However, in many of the analysis that is out there, the level of overparameterization is a bit higher than what we may use in practice. So many times we may see requirements such as the width of the network being around n squared, where n is the number of training data points. So what we're interested in asking is, what if we wanted to have a smaller level of overparameterization? And that's what we looked at in this work to try and avoid that excessive overparameterization. And we do that by emphasizing some more qualitative aspects, using only the rank of the Jacobian rather than other more specific aspects about the eigenvalues of the neural tangent kernel, for example. Okay, so we obtain a couple of results that are valid under mild overparameterization, that is in the order of n log n, or even a constant number of parameters if we have high dimensional inputs. Okay, so here's the setup. We're thinking of an input and output data set consisting of pairs. We have a tuple of endpoints in RD and another n output labels corresponding to those input data points. And we're thinking of a parameterized model that is taking parameters and input and mapping that to a prediction. Here, for simplicity, is just a real number. And we're going to collect the prediction values over the training data set into a prediction vector written in this form. And think about that as a function of the parameter data. We're going to look also, for simplicity, at the mean square error loss, where we just take the difference between our prediction and the target labels, square that, and take the sum. Some of these results are also valid for other losses, but they're just more transparent to present for the mean square error loss. Okay, one of the very simple observations, really, but that is very instructive here, is that if we look at the critical point of the loss, meaning that we take the gradient and it evaluates to 0. And if it happens that the rank of the Jacobian is n equal to the number of training data points, then that critical point by necessity has to be a global minimizer with 0 loss in this particular case. And this is actually quite simple. It's just that if we apply the chain rule to this loss, we're going to get, on the one hand, the residual, and that is going to be multiplied with the Jacobian. Now, for that to be 0, the residual has to be in the kernel of the Jacobian. But if the Jacobian is full rank, then the only vector in the kernel is the 0 vector, meaning that our predictions are equal to the target labels. And so we are perfectly fitting that data. So, if you want to understand how critical points may be global minimizers, we may as well just ask under which conditions is the Jacobian of full rank. Okay, so, and we're going to think about this from a perspective of partitioning the parameter space and studying different parts of that parameter space. In the case of, let's say in the case of a shallow ReLU network, this vector of predictions is a piecewise polynomial map of the parameters, because we have these ReLU activations that give us over any of our data points a piecewise polynomial map. And the smooth pieces for the shallow ReLU network are separated just by this condition that the multiplication of our input data point, let's say the jth one with the ith neuron input weights, this is 0, that will give us a 0 in the ReLU. And so that is the non-differentiable point for that particular neuron. So we will have a bunch of hyperplanes like this for every neuron, and for every data point, there is going to be one of these conditions. And we can capture all of them in terms of these inequalities. And so if we are not sitting precisely in one of those hyperplanes, then we're going to be sitting in a region that we may call an activation region, meaning that we look at all the neurons and whether they are active or not on all the different data points in our training data set. So this is going to be indicated by just a binary matrix. If an entry of the matrix is 1, then that means that a particular neuron is active on a particular data point in our data set. And if it is 0, then that particular neuron is inactive. So at least here for the case of the shallow ReLU network, we can look at those different pieces of the parameter space and evaluate the Jacobian. And if we take just the Jacobian with respect to the input weights, this is going to be, as a matter of fact, a piecewise constant function because the map is linear in any one of the parameters. And so it takes this particular form in here. For every weight matrix in this activation region of the parameter space, the Jacobian is constant, takes this form. Maybe the important aspect is that this depends both on the nature of the data points over here and the nature of that activation pattern. So these are the columns of that matrix A. It also depends on the output weights of the network, but I'm going to focus here on the activation pattern and the data points. And then this becomes an exercise of trying to figure out under which conditions on this input data and for which activation patterns and for which number of activation patterns, this is going to be a full rank matrix. I should mention I presented these definitions for the case of a shallow ReLU network, but similar definitions apply for a deep ReLU network. In that case, we will as well have these activation patterns now for all the neurons in the network. Now the pieces where the parameterization map is smooth may be separated by something different from hyperplanes, but it is morally a similar picture. All right, so there is here just an illustration for clarity of the subdivision of the parameter space for a single ReLU. So I am looking here at a single ReLU evaluated on 2 data points on the real line. And so we can think of, or maybe, yeah, we can think here maybe of one coordinate representing the bias and the other coordinate representing the input weight to the neuron. So we put this, we plot these data points over here. So then there is going to be these hyperplanes that determine when the neuron becomes active on each of the data points. And so we have one hyperplane for each of the 2 data points, and they together split the parameter space. Maybe in this part of the parameter space, the Jacobian is full rank, and this part is mapped in function space, in the space of predictions, to a full dimensional set of possible predictions. Whereas this red region here, the Jacobian has rank 1. So we are inactive on one of the 2 data points. On the data point, the first data point, we are inactive. And so we're just changing the value over the second data point. So the prediction value on the second data point is changing, but it remains 0 on the first one. Similarly, on the green region, we just move along this part. And the blue region, the neuron is inactive on both data points. And so the prediction value is just 0 for both of the data points. If we then had multiple neurons in a layer, then we will get some kind of a product of this arrangement, because all of the neurons operate independently of each other. But it's a similar picture. So we're interested sort of in how many of these pieces of the parameter space will have a full rank Jacobian. That will depend on the nature of the data set. Yeah. All right, so this is our first observation. It's about the number of activation regions that are good in the sense that they have a full rank Jacobian, and in turn such that every differentiable critical point in those regions is in fact a global minimum of the training loss. So if we fix some epsilon greater than 0, and if we stipulate that the size of the layer, this is for a 1 hidden layer ReLU network, to be larger than n over the input dimension, n is the number of training data points, or larger than log n divided by epsilon t0, then for any generic data set, it will be true that at most an epsilon fraction of all the activation regions has a full rank Jacobian. So the condition here that D1, the width, is bigger than n divided by D0, this is essentially saying that the number of parameters is at least as large as the number of data points. And this is certainly necessary for us to be able to have a Jacobian that has rank n. And this other condition over here it comes from properties of random binary matrices. And it's the statement that if you have a sufficiently large IID binary matrix, then it will be full rank with high probability. And that's where we get this epsilon sitting in here. All right, so this is fine with a caveat. And the caveat is that we are making here a statement about these activation regions without saying much about whether they are empty or not. we're just thinking about these binary matrices that say, some neurons will be active on some data points, but it's not necessarily clear that those activation patterns will in fact be feasible for any choice of the parameters. So therefore, next, we need to focus on the non-empty activation regions, those that are feasible. And here for the case of a shallow ReLU network, that's not too bad because we have this arrangement of hyperplanes, as I was mentioning. If we have multiple neurons, we get this product of hyperplane arrangements, and there is a very well-developed theory for that that we can leverage. So in particular, if we have that the data points are in general position in some d-dimensional space, then we can exactly enumerate how many activation regions will be non-empty. And this is precisely a number. This can be recovered by Zaslavsky's theorem for the case of points in general position. If they are not in general position, we can use other formulas to enumerate those. But for data, typically will be in general position in some affine space. We get here a power D1 because, as I was explaining, we have a product arrangement. And okay, so that's fine. Next, when we want to think about the rank of the Jacobian, it's not only that we want to know how many different activation patterns are possible, but we're going to collect them or combine them together across different neurons. And after stacking them together, we want that this matrix is of full rank. And so in order to have that, we also need to know what those binary vectors are. So we need to know what is the identity of the non-empty activation patterns. This is a little bit more complicated and less well understood. But so there is a nice geometric description for them, and it goes like this. So if we take this Minkowski sum of certain line segments defined in terms of the data points, this will define a polytope, and the normal cones of the vertices of that polytope are precisely the activation regions in parameter space that are non-empty. Maybe for people from a combinatorial background, this would be combinations of covectors of the oriented matroid of the input data. Picture is like this. We put all our data points over here, x1, x2, x3, in an affine space with the first coordinate being equal to 1. And then we take all the sums of those points and take a convex hull. And the points that are vertices, those would be the patterns that are feasible, and the normal cones will be the non-empty activation regions in the parameter space. This is for a single neuron. We have multiple neurons, and we get a product of this kind of arrangement. One implication of this is that if we have a high-dimensional input space, all the activation regions will be non-empty. And in that case, we immediately get this corollary that in all but at most an epsilon fraction of all the non-empty activation regions, every differential critical point is in fact a zero loss global minimum under the same conditions as the theorem before. And that is if the input space is of high dimension. We can also look at other cases that we can catalog very explicitly, such as one-dimensional data. For one-dimensional data, all the activation patterns are very simple, are just some kind of a step function. And so we can study them very explicitly. And in this case, we have this statement. If D1, the number of hidden neurons, is larger than n log m divided by epsilon, then in all but at most an epsilon fraction of the non-empty activation regions, the Jacobian is full rank. And the same conclusion, every differential critical point is a global minimum. So for this, we use a coupon collector argument where we are trying to collect a good set of activation patterns, and we need to calculate the probability that a certain collection of a certain size does not include a good set of patterns, meaning that it is a full rank matrix. Okay, that's the argument. We can also ask, we are sort of excluding the possibility that there is going to be a bad local minimum in one of the activation regions, but you may also ask how many of those regions of the parameter space do in fact contain global minima. And here is an answer. If we assume that we have n log n divided by epsilon neurons that have a positive output weight and an equal number of neurons that have a negative output weight, then in all but at most an epsilon fraction of the regions, we will have a global minima, and the set of global minima is going to be an affine set of codimension n, as you would expect. So we are perfectly fitting the data. Every data point that we're fitting represents one equation in the parameter space. So fitting n data points means that we have a solution set of codimension n. All right, so this is good. It's saying that a lot of the regions actually have a high dimensional set of global minima. Next, one question that one may ask is, especially in the case of ReLU networks, many of the critical points may not in fact be differentiable. So we're making an argument based on the Jacobian, but at those intersection points between the smooth pieces of the parametrization map, it may be that many of our critical points are sitting in there. But we can extend the argument and draw conclusions for that case as well. So the idea is to use a subdifferential and say that if we have a subdifferential 0, and that's the condition that we need. Here is the theorem. So again, same condition. If we have that the width is n log n divided by epsilon in all but at most an epsilon fraction of the regions, every local minimum is going to be a global minimum. And it may be, in this case, we are not requiring that this is a differential critical point. Okay, the other natural question is what happens in the case of deep networks. For this, as I was mentioning, the setup is a little bit more convoluted, but not very different. We now have a deep network. We start with the input, and then we compute our activations at every layer, and we have a linear output here. In this case, the activation patterns are given by tuples of binary matrices, one of them for every layer, and indicating whether those neurons in the layer are active in which data points. And we have similarly these subsets of parameters where the network follows a particular activation pattern, and over those pieces, the parametrization map is smooth. Here is an extension of the previous result for the case of deep networks. Here, the condition is as follows. We ask that the width of every layer is going with log n divided by epsilon L. This is a mild requirement if you think about it. So a width being log n is relatively narrow. And we're going to have the last layer to be of linear width in the number of data points. So for the last layer, that's the point where we require that this has size n. If this is satisfied, then for almost all of the regions, our condition will hold that the Jacobian has full rank. And therefore, the critical points will be a global minimum. All right, another question that one may ask is what happens with the volume? So it could be that some of these regions of parameter space are good, but maybe they are very small in size, and the bad regions are very big in size. So we studied here also what happens in terms of the volume of those regions. And now, since this partitioning of the parameter space is being defined in terms of the data, the volume of those regions depends on the particular properties of the data. So imagine that your data set has points that are very clumped together. In that case, it's harder for a hyperplane to split those points. So it is natural that these regions are going to be bigger if the data is separated in some sense, and therefore the property that we require here is some type of anti-concentration. We define it in this particular way, but there are other definitions that may be possible. So we define some anti-concentration property for the data, and given that, so So we have an epsilon and a gamma capturing this anti-concentration. We have a generic data set that satisfies this anti-concentration property. And then we have a lower bound on the width of our layers, goes with log d0 divided by epsilon, or with n divided by d0, and scales inversely proportionally with this anti-concentration parameter. Then with high probability, at least 1 minus epsilon, our Jacobian is again full rank. So this is now looking at the volume of the regions where this Jacobian is of full rank. Okay, we also ran a couple of experiments to try and get an idea of this theory in practice. So in these figures, what I am showing is the x-axis is the data size, so that's n, and the y-axis is the width of the network. That's what I was calling D1 in most of the slides. And from theory, what we expect is that there's going to be a line, a linear function between the width and the data set size that separates the cases where the Jacobian is of full rank. So we run this for different input dimensions, d0 equals 1, 2, 3, 4, 5, etc. And we see that indeed, so in this plot, blue means that the probability of the Jacobian being of full rank is low, and yellow means that the probability of the Jacobian being full rank is high. So we sample a bunch of parameters or different activation regions, evaluate the rank of the Jacobian, and we see that indeed there is some kind of a linear, let's say, boundary between those two regimes. This is consistent with the theoretical statement. And this next figure, similarly, we have here the size of the data set and here the width of the network, but now we're also scaling up the input dimension with n. And when we do this, the expectation from the theory is that there's going to be a horizontal line determining that transition. And indeed, in these figures, we see sort of a horizontal line determining that transition. And next experiment, this is a percentage of regions that have a global minimum. And here, the theoretical statement is represented by the dashed line. It's a transition between most regions having a global minimum versus most regions not having a global minimum. So the different figures here are showing different target functions. So the bottom right is maybe the most indicative one for the theoretical statement. This is for random data. Random data should intuitively be hardest to fit. And here the transition is close to the theory. The other figures are showing data that comes from polynomials here of degree 10, a quadratic polynomial, and a linear function. And we see that for those simpler functions, it seems that it is a bit easier to fit that data perfectly, even if the width of the network is smaller. But those are not part of the theoretical statement, let's say. But this one, but still, you know, they still seem to indicate a linear boundary between the two settings. Okay, so we can run this experiment as well for higher dimensions. In this case, the width of the network doesn't have to be as large to get to that transition. So for high dimensional inputs, we of course expect to have more flexibility to fit that data, and that's also what we observe here in the experiment. Okay, let me wrap up. I'll give a quick summary. So we have studied here the loss landscape of ReLU networks in the mildly overparameterized regime. And we could observe that most activation regions in parameter space have no but differentiable local minima. For the univariate case, we made this more specific. And we could also show that most of the non-empty activation regions contain high dimensional sets of global minimizers. We obtain extensions to non-smooth critical points, deep networks, and also evaluating the volume of those regions. Now, there are many other topics that we're looking into at the moment. We have done previous work on the neural tangent kernel, bounds on the least eigenvalue, optimization, but now making statements for the mildly overparameterized regime remains an interesting frontier. So we're currently looking at range descent and biases of optimization algorithms and statements about generalization. Okay, so I'm going to stop here.
Thank you very much. Are there any questions or comments?
Oh, thanks so much for your talk. I was wondering what happens when the ReLU networks become, for instance, you can change them a little bit, like leaky ReLU or maybe other sort of activation functions. Does your theory also hold in such cases?
Yeah, great question. Leaky ReLU tends to be a little bit easier to study because you don't have dead neurons. But yes, indeed. A lot of this, let's say, the composition of the parameter space will be quite related. Again, there are differences because you don't have dead neurons for the case of leaky ReLU. But yeah, so a similar discussion could be conducted especially for piecewise linear activations, but actually any piecewise polynomial activation could be also investigated.
Thank you. So any other questions?
This is Taiji. So thank you very much for your interesting talk. So could you give us some comment about the connection to some optimization, like a gradient descent? So then what kind of thing your result indicates about the gradient descent?
Yeah, that's a great question. Yeah, for sure. Well, a lot of the advances in the optimization for neural networks have been based on the, let's say, a neural tangent kernel perspective, where we look at the empirical neural tangent kernel at initialization, and we try to bound the least eigenvalue away from 0, and then discuss that this kernel is stable during training. So the least eigenvalue being bounded away from 0 is equivalent to a Jacobian being full rank. And so a lot of this analysis can serve as a basis to investigate bounds on the least eigenvalue of the neural tangent kernel in a mildly overparameterized regime. And in cases where we want to make that a little bit more depending on the structure of the data, that is in fact something that we are investigating at the moment. So that's if you wanted to take this NTK perspective. But another interesting option is actually to look at the trajectory of the parameter along these different smooth pieces of the parameter space. And in a sense, what we now need to control is, not necessarily this notion that how is this eigenvalue moving or how is the kernel moving, but how quickly are we going to be able to fit the data versus how quickly are we escaping from one of the smooth pieces of the parameter space. So it's an interesting trade-off there to investigate. That's something that we did not do in this paper, but it's something that we're very interested in and taking a look at the moment. So it's a balance between these two parts. Right. So yeah, so there are connections from the side of investigating the spectrum of the NTK for this mildly overparameterized regime, making it more data dependent. And from that perspective, combinatorial trading off between the time that it takes to fit the data and the time that it takes to escape one of the good regions. In practice, many times you will jump across different regions of the parameter space, and that's not a problem so long as you remain in regions of parameter space that have, for example, full rank. But some intriguing possibilities are that you're going to jump into regions that have low rank and still at the end be able to converge to a global optimum. That's a very interesting line of investigation, in my opinion.
Okay, thank you. Thank you very much. So if no other questions, we thank our speaker again.
Thank you.
Thank you, Guido.
Okay, let me start my talk. So thank you for inviting me to the workshop. I'm Atsushi Nitanda. So today, I'll talk about the mean field optimization with its convergence rate analysis. Mean field optimization includes a mean field range band dynamics, so which was also presented by the talk, by the Professor Taiji Suzuki's talk. So the mean field optimization is the problem defined over the space of the probability distributions. A typical example of this problem is training a two-layer neural networks under mean-field regimes. So it looks like this. And we simply call this model mean-field neural networks. In fact, this model is very simple. However, so this model has been actively studied recently because its preferable properties like global convergence to the optimal solution and high adaptivity to the given target function, which is also believed to be a very important property to bring out the performance of the neural networks. To optimize this model, so we usually employ the stochastic gradient descent or its variant. In this talk, so we mainly consider the noisy gradient descent, which is the gradient descent plus Gaussian noise. And previous study, May et al. So showed that this optimization method can be described by the mean field range-bound dynamics in the continuous setups in terms of the time and the space. And some studies also proved the convergence to the mean field range-bound dynamics to the optimal solution of the entropy regularized objective functions. However, the convergence analysis of this method is generally challenging, and we basically need strong assumption, especially when showing the convergence rate. However, so we developed some theory to prove such convergence under milder assumption with simpler proof techniques. So this talk presents some result along this direction with some other optimization method for mean field problems. Okay. So before going to the details, so let me explain a bit the motivation behind the study. So to optimize the neural networks, so we usually run the gradient descent. Then it's well known that gradient descent converges to the stationary point. And then, so for neural networks, the gradient descent can get stuck at the poor local minimum because of the non-convexity of the loss landscape. However, so many empirical studies demonstrated the gradient-based method converges to near optimal solution despite the non-convex loss landscapes. So many studies tried to unveil this phenomenon. To do so, some theories like neural tangent kernel and the mean field analysis have been developed in the literature. In this talk, so we focus on the mean field analysis. So what's the mean field optimization problem? So the objective function L of Q is defined over the space of the probability distribution. So here, so Q represents the distribution defined over the Euclidean space, like so RD. So then the objective function is sum of FQ plus negative entropy term. So the latter term is basically regularizer. And then in this talk, we suppose F of Q is convex functional. So over the space of distributions. So FQ satisfies this inequality. So this means convexity in the L2 sense. So here's, so any given Q prime and Q, so FQ prime is lower bounded by FQ plus linear approximation term. So in fact, so this last term is a linear approximation to the objective function F. So basically, so delta F over delta Q represents the first variation, so which is defined in the same way as the Fresh differential. And then, so this term is regarded as an inner product between the gradient in the space of the distribution and the perturbation in this space. So especially when, so considering the directional derivative of F along the direction tau, so then this directional gradient satisfy this equation. So the left-hand side is characterized as the inner product between the first variation and the direction R. Okay. So next, so I'll explain the example of these mean-field optimization problems. So we consider this kind of the two-layer neural networks. So M is the number of hidden neurons, and R represents the index of the node. Then, so H theta X is one function of this neural network. So here, A represents the parameter for output layer, and B is the parameter of the input layer. Then, so we can write A sigma B X as the H theta X. Then, so we prepare M neurons from sheet 1 to sheet M. So then, so these two-layer neural networks can be described by the average of H theta X. And then we suppose each particular sheet R follows the distribution Q. Under this condition, so let's take the limit of the number of neurons, and then we arrived at the integral form of the neural networks, so like this. So this model has infinitely many neurons, and so this is integrated with the distribution Q. As introduced in the Suzuki Sensei's talk, so the remarkable point of this modeling is the linearity of the model with respect to the parameter Q. In fact, so originally, the learning problem of the neural network is non-convex with respect to the parameter theta R because of the nonlinearity of the activation function. However, so in this mean-field limit, we can consider distribution Q as parameter of the model. As a result, so this model is a linear. And the learning problem becomes a convex optimization problem for typical loss functions such as squared loss, logistic loss, and so on. So example of the loss function. So in this case, the objective function is risk. So like this. So L is a loss function, and XY represents the data random variable for data distribution, and we impose the L2 regularization. Then we can calculate the first variation of objective function f of q, so like this. And to optimize this model, so we consider a noisy gradient descent. So that's a gradient descent plus Gaussian noise. So this term is the gradient of the loss part, and this first term comes from the L2 regularization. So that's a weight decay, and we add the Gaussian noise, so theta k. So capital theta is all the pairs of the theta r from theta 1 to theta m. So then, so if we focus on the update of each particular theta r, so then we obtain this update. So this small theta r is just a component of capital theta. So then we obtain this update for each particle, each neuron. Then we take the mean field limit, and that is the limit of m, so goes to infinity. And we also take the limit with respect to the step size eta. So then, so we obtain this stochastic differential equation, which is so nonlinear Fokker-Planck. This is called so mean field range-bound dynamics in continuous setup. And this term is basically gradient of the first variation of f. And this term is called Wasserstein gradient in the literature. Okay, so by taking the continuous limit of the noisy gradient descent, we can obtain this kind of SDE called mean field lunchbound dynamics. Okay, so let's go back to the general mean field optimization problem. So to optimize objective function L of Q, so we consider this kind of the update for each particle theta, so like this. And then, so Qk is a probability distribution of a particle theta k. So this is a general form of the noisy gradient descent, so as I explained. So then by taking the limit with respect to the continuous time, so we obtain this mean field lunchbound dynamics for general optimization problem, so of L of Q. This SDE describes the evolution of each particle, so like this. So then, so the probability distribution of theta t is also evolving, so following some dynamics. And then, in fact, we can obtain so this PDE, so which describes the evolution of the distribution QT. Then, so by studying this dynamics, we can show the convergence of the mean field lunchbound dynamics. So as a result, so we can give some guarantee for noisy gradient descent by taking into account the approximation error in time and space. Okay. So to explain the difficulty of the mean field lunchbound dynamics, so I'll compare our problem setup with its special case, so the left-hand side. The right-hand side is a problem setup, so we consider then, so we replace this convex functional term f of q with linear functional EQF. So this term is a linear functional in distribution Q. Then, so we can specialize mean field lunchbound dynamics so to that in this linear functional case, and then we obtain the normal lunchbound dynamics. So in fact, so we can easily confirm so that the lunchbound dynamics is a special case of the mean field lunchbound dynamics because first variation of f is just a small f in this linear functional case. And then, so by taking the gradient of this first variation, we obtain the update of the lunchbound dynamics. So what's the difference between these two equations? The main difference is the drift term, which defines the direction of each particle to evolve. So let's take a look at the left-hand side. So the drift term of the lunchbound dynamics is the gradient of f. So like this. So this means that so we can simulate the lunchbound dynamics with only one particle because the drift term depends only on the particle position of the particle like this. However, so in our general setups, so we need multiple particles to simulate this dynamics because the drift term depends on the distribution itself, so Qt, as well as the position of the parameter theta t. So we essentially need many particles to approximate this mean field lunchbound dynamics. And this difference so makes additional difficulty to analyze. However, so we resolve this difficulty by considering the proximal Gibbs distribution defined like this. So this distribution is a key to our analysis, as I so briefly explained later. And then, so we can show the convergence of the mean field lunchbound dynamics, so using the property of this distribution. And moreover, so we can obtain the convergence in the fully discretized setups in time and space. Okay, so let me briefly explain the proximal Gibbs distribution. So given distribution Q, so we define its associated distribution PQ like this. So this is a Gibbs distribution, so whose potential function is minus 1/λ and times first variation of F. And this Gibbs distribution can be also characterized as the solution of this problem, like this. So here Q prime is a variable of this problem. So and this term is a linear approximation of the objective function L, and we impose the proximal term, so KL divergence between Q prime and Q. So which forces the Q prime close to Q. And then, so because this problem is an approximation to the original objective function L, so PQ should be close to the optimal solution of LQ, so in some sense. So this is, so PQ is basically proxy to the solution. Then, so I'd like to explain the intuitive motivation behind the mean-field range-bound dynamics. So let's consider the evolution of the mean-field range-bound dynamics QT. So QT is an evolution defined by the mean-field range-bound dynamics. And then, so PQT is an evolution of its proximal Gibbs distributions. And PQT is so characterized as the solution of this problem. So then, so we consider this mean-field range-bound dynamics like this. So then, so we notice that this dynamics is a range-bound dynamics for this Gibbs distribution. So at the moment time t. So because so this drift term, so gradient of first variation of f is a gradient of this potential function of PQT. So this means that so mean-field range-bound dynamics is a momentary range-bound dynamics for PQT. However, so in fact, so mean-field range-bound dynamics is different from range-bound dynamics. So because this potential function is also changing so along the dynamics of the distribution. So this is just a momentary range-bound dynamics. Okay, so in other words, so along mean-field range-bound dynamics, so distribution QT, so try to follow its Gibbs distribution PQT, so like this. So as depicted so in this figure. So then eventually we can expect so both distribution QT and PQT so meet each other at the end point. And so previous work, so Hu et al. Proved that the Q equal PQ is a optimality condition for the optimization problem. So then, so we can expect so mean-field range-bound dynamics can solve the objective function, so minimization problems. So this is just an intuitive understanding of the mean-field range-bound dynamics. Indeed, so we can justify this intuitive explanation so using the some property of the proximal Gibbs distribution and some assumptions. The most important assumption is the uniform LSI. So for any given distribution Q, so we suppose the proximal Gibbs distribution PQ satisfy this inequality with constant alpha. The right-hand side is the Fisher divergence between Q and PQ. And this right-hand side so appears in the directional gradient of the objective function along the distribution, along the mean-field range-bound dynamics. So the right-hand side is basically a gradient north of the objective function along the dynamics. And the left-hand side is the divergence between Q and PQ. So as I explained, so the optimality condition of the problem is that Q equals PQ. So then, so the left-hand side doesn't vanish unless so Q is the same as the PQ. So this means that the optimization process doesn't vanish as long as so Q doesn't converge to the optimal solution. So then, so we can show the convergence of the mean field large band dynamics. So based on this assumption. Then, so this assumption sounds strong. However, we can guarantee this assumption. So for training mean field neural networks under some condition. So for instance, we can utilize the Holy-Stroke argument or Miklós-Tulik or Lipschitz perturbation argument to guarantee this condition for two-layer neural networks. So especially when the first variation delta F delta Q is sum of the bounded function or Lipschitz continuous function, so plus so strong convex function, then we can guarantee the uniform LSI with some constant like this. So indeed, so we can derive the simple proof using this assumption for mean field large band dynamics. So here, so Qt is the evolution of the mean field large band dynamics. And then, so we proved this inequality. So the left-hand side is the objective gap between LQT to LQ star. So Q star is the optimal distribution. Then, so this gap so converges to zero exponentially fast. So T is the time step. So this means exponential convergence to the solution. And the proof is also very simple. So like this. So let me quickly explain this proof. So first, so we take the gradient derivative of LQT like this. So then we obtain this equation, so which is kind of the chain rule. So for this problem, so this is the inner product of the between the first variation and the direction of Qt. Then so yeah, applying the definition of the mean field large band dynamics, we obtain this equation, and we obtain the next equation by using the partial integral. So for this divergence term, and then so we obtain this equality. So by simple calculation, and then we obtain this inequality. So using the uniform LSI, and eventually, so we obtain the last inequality by using the entropy sandwich, so described here. So we proved the optimality gap so can be upper bounded by the Kerr divergence between Q and PQ, so like this. This is also our contribution. And then so we obtain so this inequality. So this means that so as long as so LQT is not optimal value, so its gradient is strictly negative. So as a result, so we can expect the convergence of LQT, so by applying the Grunwald techniques. So yeah, the proof is quite simple. So far, so I explained the situation of the continuous time. However, so we are interested in the convergence under the finite particle setups and discrete time setups. So in fact, so we can extend this result, our result, to such a situation. So in fact, so we usually simulate mean field large band dynamics using finite M particles like this. So from theta R1 to the theta M. So then, so far, so we consider all particles separately. So because so theta r is one particle of distribution. However, so next, so we group all m particles into one parameter, so capital theta again. Then we obtain this update. Okay, so then, so we notice, so this update is just normal Langevin dynamics for particle capital theta. So then, so I'd like to explain again. So the upper side describes the mean field Langevin dynamics with m particle. So we run m particle simultaneously. However, so if we group all particles into one capital theta, we obtain the normal Langevin dynamics with one particle. So then, so we can recognize this update is normal Langevin dynamics for this Gibbs distribution. So exponential minus m over lambda times f. And the parameter is capital theta in this case. And in fact, so to show the convergence of this normal Langevin dynamics, we can apply the existing theory for Langevin dynamics. However, so naive application of the Langevin theory leads to slower convergence rate because so the LSI, so log Sobolev constant of this Gibbs distribution is getting weak. So as the number of particles goes infinity. In fact, so in the case of the L2 regularized case, so the LSI constant of Gibbs distribution is scaled inversely with the number of particles. So as a result, so we cannot show the convergence of this Langevin dynamics when taking the limit of the number of particles. So we need, however, so as I introduced, so by taking the limit, so we arrived at the mean field Langevin dynamics with provable convergence guarantee. So this sounds a contradiction. Yeah. Naive application of Langevin dynamics leads to poor convergence. However, so by exploiting the structure of this Gibbs distribution, so we can guarantee the better convergence to the optimal solution. So like this. So this is a result also obtained by the Suzuki, Wu, and Nitanda. So this part represents the gap between the objective function Lm, so solved by normal Langevin dynamics. And then we can show the convergence, so like this. So the first term is an exponential convergence term, and the last term is coming from the discretization error in time and the finite number of particles. So the remarkable point of this discretization error is the dependence on the number of particles m. So in fact, so if we apply the naive evaluation for particle approximation, we obtain this kind of the exponential blow up in time. So approximation error using the caused by the finite particle, so blow up exponentially like this. However, so we can avoid such an exponential blow up by using the techniques derived by Chen-Ren 1 and 2022. So yeah, this is our contribution. Moreover, so let's quickly introduce another perspective of the mean field optimization problem. So let's consider the finite sum optimization problem setup like this. So L of Q is sum of the empirical risk plus regularization. Then, so we can apply Fenchel duality to this problem setup because the problem is convex with respect to the distribution Q. Then we can obtain the dual objective like this. And then, so by the strong duality theorem, so we can see the equivalence between the optimal value of primary objective function LQ and the dual objective like this. And moreover, so we can prove stronger results like this. So GQ is a dual variable, so associated with the primal distribution Q. So then, so we can show that the Kerr divergence between Q and Gibbs distribution PQ is exactly the same as the primal dual gap, so like this. So as I used in the proof, so Kerr divergence between Q and PQ upper bounds the objective gap, so primal objective gap. However, so in this theorem, so we can see that the Kerr divergence is exactly filling the primal dual gap, so like this. Okay. So in fact, so by using the property of this kind of structure, so we can guarantee the convergence of the Kerr divergence between QS and its proximal Gibbs distribution like this. So as I explained, so this Kerr divergence measures the optimality gap, and we can guarantee the convergence to 0, so like this. Okay, so I'm going to end the talk with introducing some other mean field optimization problems. So in fact, so mean field large-one dynamics try to minimize the Kerr divergence between Q and PQ. So however, so we can derive more direct method to minimize the Kerr divergence like this. So this is a dynamics of the entropic fictitious play, which was introduced by Chen 1, 2023, and we can guarantee the convergence of this entropic fictitious play, so using our primal dual framework, so like this. So we can show the exponential convergence of the Kerr divergence, which is same as the primal dual gap. And we also derived the method which aim to minimize the dual objective, and we obtain particle stochastic dual coordinate ascent with exponentially fast convergence guarantee. And finally, so I'll end the talk with this method. So the naive way to derive the optimization method is that so we approximate the objective function, and we impose some regularization, so like this. So this is the approximation problem to the original objective function f plus Kerr regularization, which makes the next step close to the previous steps. And then we obtain this kind of the update, so like this. And by expanding Qt, so recursively, we obtain this kind of the equation. And then, so we arrived at the dual averaging method. So in fact, so we can approximate this intermediate solution Qt plus 1, so by learning some sampling method like the large-one dynamics. And then, so we obtain the particles so which approximate this distribution. And so in fact, so we can show the convergence for this procedure. So, okay. So this is a list of related literature. Okay, so let me end the talk here. So thank you.
Thank you very much. The schedule. So I would encourage our audience to communicate with Professor Nitanda afterwards by email or some other methods. Yeah, so thank you very much again for your nice talk.
Thank you for the introduction. I'm Akiko, and I'm working, my main affiliation is the University of Tokyo, and also I'm leading a team, continuous optimization team at AIP Center here, RIKEN. And this is joint work with my student, master student, Nozawa, and also Pierre Louis, RIKEN AIP, my member. Okay. And then, yeah, this is just excuse. I'm a bit different from what you're doing. I'm working on mathematical optimization area. So I get research motivation from machine learning, but mainly my target of my publication target is for optimization journal, mathematical optimization, SciAm journal optimization or something. But I'm always motivated by machine learning. So I'm so happy to be here, and so thank you for including me here. And yeah, so this workshop name is deep learning, but yeah, my deep learning concept just appeared in the last of my talk. So I did a numerical experiments using this one support of my student, but yeah, don't ask me the meaning of this one or problem setting. But I use my motivation is to reduce the decision variable size. So of course, stochastic gradient descent method. It's the method to decrease the number of samples. But I'm more interested in decreasing the size of a decision variable. So yeah, this is the thing I want to introduce in this talk. So want to decrease the dimension of the decision variable X. So I'll go to the general problem setting. So suppose that we have a function and decision variable size is n. And yeah, here we assume that the function is differentiable. So this is the problem setting. And usually, yeah, we construct an iterative algorithm for solving a problem to find a stationary point for non-convex problem, maybe global solution for convex cases. But yeah, D is called descent direction. And yeah, so suppose that we have already xk, point xk, and try to find the best such direction at xk point. And then of course, this problem is almost difficult like this. But yeah, but so we usually give up solving this one exactly. Instead, we linearize or approximate function f at xk point like this. So we use Taylor expansion up to 1 degree, then linearize like this. And this problem can be solved easily by a closed form solution like this by using some step size. And if we use Taylor expansion up to second order, then this function will be approximated like this. And then, easily we can get a solution like this. So this direction is called steepest descent direction, and this method is called steepest descent method or gradient descent method. And for this case, Newton method for strongly convex case, if we can take an inverse operation for this part, this is called Newton method. So it's a very elementary stuff for you. So let's move to subspace method now. And here we generate random matrix here. So you can assume fat matrix. S size S is the reduced dimension S. And N is original space. So you can imagine very fat matrix. And if we transpose for matrix PK, then U. Now decision variable is U, and the size of the decision variable becomes S. So pretty much smaller than original space N. And this is the idea of random subspace algorithm. So update, compute, update UK from now on. Then again, if we approximate this function up to the first order, then we get this linear function, and then easily we can get such direction, best such direction, minimizing this linear function. And this is the second order algorithm for convex case, strongly convex case. So it's called subspace Newton method. And here of course, to calculate subspace gradient direction, we should not separate these computations separately because later I will discuss about it more, but we should combine this operation together, PK, gradient F in a product that we should do together to save our computation task. And this one, it may be easier to understand the benefit of this subspace method. So I think to use this method, we assume that Hessian operation is easy. Hessian computation is easy, but inverse operation is very expensive and to the cube or something. So yeah, so in such a case, PK, matrix PK can reduce the matrix size from original n times n to s times s. So we can save our cost to compute inverse operation of computation here. So this is the motivation of using second order method for this optimal problem. Okay. Yeah. So I will introduce existing method using random subspace algorithm. So yeah, as I said, the decision variable is now U, space U, S-dimensional vector. And if we squeeze, put this one into here, we can get an update formula. So this is the here update rule. And this first order random subspace first order method was developed by Zhang for the first time in our research area for strongly convex case. So they proposed this algorithm and proved the convergence rate only for strongly convex problems. After that, they provide generalization algorithm. So yeah, so subspace first order methods are something like this. And as I said, we should compute this one all together like this using finite differentiation. Of course, if we use h to the fixed some amount of small fixed value, we have error, approximation error for this. But these guys, this group also evaluate the gap, approximation gap from this one and this one, including those gaps. They provided theoretical guarantee convergence to a stationary point. They discuss about the speed. And if function evaluation is difficult, expensive, then this method works well because the number of function evaluation can be reduced from n to s. So this is the benefit beneficial when function evaluation is expensive. Okay. And let's move to the existing. Yeah, so it depends on the situation. So optimization problems sometimes not necessarily we can compute Hessian easily. So in such a case, we can use this one. But maybe difficult machine learning problems, maybe we should not compute this one and we should. For this case. Sorry, I mixed several methods in this talk, and from now on, my research is based on this first order method. But I did some developed algorithm based on this approach. So I just explained the benefit when we use this one. Maybe we can use this approach when gradient computation is so expensive. For example, convolution neural network, we should use this one. If problem is not so large and gradient or Hessian computation is not so expensive, then maybe this approach would be good because we know that Newton method works very fast if this calculation is possible. But still, there is an advantage of using this method because inverse operation is easy. So different applications in our mind. So maybe I'm talking about several applications in my mind and different if function gradient is extensive, we should use. Just this one is to reduce the cost of inverse. Please stop me if I can explain well. Give me a question anytime. Yeah. Yes. Yes, that's right. That's right. Like this. Then, yeah, this vector S dimensional vector. So number of evaluation for function evaluation is smaller than this one. So yes, when we use Kodak method, we should use this finite differentiation. And then, but this subspace, random subspace algorithm, the sequence of this research started from second order algorithm. Maybe Grover et al. They started this approach by using random matrix, and yeah, every iteration random matrix are changing. And yeah, they proposed this kind of random subspace algorithm for the first time for convex problems like this. And then yeah, of course there is a discussion. Hessian computation is costly or something. So after that, BFGS more easy approximate Hessian approach was proposed by them. But top three algorithms are for convex problems. Later, yeah, to be honest, this is our research project. We decided, okay, let's provide, develop a random subspace second order algorithm for non-convex problems for the first time. This was our research target. But at the same time, in the same year, several groups did similar work. But yeah, from 2022, non-convex algorithm for non-convex problems are proposed. And okay, yeah.
In nonlinear least squares, there's a lot of this kind of method.
Non-linear. Oh yeah, yeah. But it's a sample. Just some. This is for reducing the sample size, not decision variable. Yeah. So
I know about nice from method. 20 years.
Oh yeah, yeah. But yeah, it's very close. But iteratively apply to reduce the existing method. It is the difference. And also the problem setting is, yeah. So yeah, you're right. I should put the research results earlier. Yeah, you're right. It's so connected. Yes, thank you. Yeah. So earlier, so for specific problems, yes, there is. Yeah, yeah, that's right. That's right. Thank you. Okay. So this is the, yeah, recently there are lots of papers in the same year with the same target, random subspace algorithm for non-convex problems. So yeah, this is our results and iteration complexity. This means that, yeah, how many iterations is necessary to find a epsilon stationary point. So this is the number of iteration, and also this algorithm seems good, but we could show the local performance. So locally, our approach can achieve the superlinear convergence rate. So something like this. So this is the comparison, and some approach can find a second order stationary point or something. So we are computing each other in the same year. And yeah, this is the main topic. Sorry, I took a long introduction part. Sorry. From now on, I move to constraint problems. Okay. Yeah. So this is the constraint optimization problem. C is the constraint. Our case, we don't need to give this assumption convex feasible region, but Cartes. So this also we saw that, oh, it must be interesting to provide a random subspace algorithm for constraint case for the first time. But we realized that in the same year, again, another work, similar motivation also was proposed by Oxford University. And also, but their approach is to need to solve this non-convex optimization problem globally, each iteration. Of course, yeah, this constraint problem is a bit problematic because we need to care about this feasible region all the time. But yeah, they assume that they can find a global solution for non-convex problem. But our approach does not need to assume such a big thing. So as I introduced, it's easy to develop random subspace algorithm because if we replace decision variable by such direction D by this one, any algorithm can be considered as a random subspace algorithm. So it's easy, just replace such direction part D by this one. Then we can get random subspace algorithm. It's easy to develop it. But theoretical guarantee is difficult. Theoretical guarantee means that our algorithm can the convergence point of our algorithm is a stationary point or something. And if we can find a stationary point in the end, then how much iteration is necessary to get an epsilon approximate stationary point. So iteration complexity is also important. Those things is difficult to prove, but we can use this important using this lemma. We can prove it because this is a random matrix, and this lemma implies that we can preserve the norm of any vector with a high probability. So we can bring this topics into a high probability discussion. Then, yeah, we recently did this kind of work, but I more focus on subspace gradient method for convex constraint optimization in this talk by using the remaining time. And so as I said, the research question is something like this: how many iterations are necessary to find an epsilon stationary point for unconstrained case, or KKT point for constraint case? Constraint case, the criteria is KKT. KKT condition is necessary criteria we need to satisfy, like stationary point. We don't, of course, this case easy because gradient need to be gradient of f need to be 0. It's easy, but constraint case we need to consider about the constraint like this. So this so KKT condition is necessary to guarantee that our solution is okay because it satisfies KKT condition. So yeah, so this is our problem right now, and we assume those thing ordinary assumption. And here maybe in machine learning area, constraint would be regularizer fairness constraint or non-negative constraints or something like this. And so it's a side effect of using a random approach. Luckily, we could prove that we can take a longer step size by moving the subspace because this is a surprising observation for us. So constraint case usually of course the difficulty of dealing with constraint case is the case the optimal solution or stationary point exists on the surface of the constraint. Then when we develop an algorithm, the sequence tend to be on the surface, and for example, move, calculate the search direction, that projection onto the surface again, and then the step size tend to be very small. Move and projection, move, projection. So tend to be very small. But by moving a subspace inside of the feasible region, we can calculate the sequence more large step. So it is a very good observation for us. And yeah, so I will explain the only linear constraint case to make this discussion simple, but we can deal with a non-linear constraint case too. And we can see our approach can be a random subspace variant of gradient projection method. So, yeah, and we provided worst case iteration complexity and something like this. And what is gradient projection method? It's a very simple approach developed a long time ago. Just calculate a gradient direction, steepest descent direction, and projection onto the surface. That's it. So it's a such direction. So if we, of course, the step size can be, we need to pay attention to the size of step size because otherwise we will be beyond the feasible region. But we can keep in the surface by projecting the such direction on the surface like this. Okay, and this is the KKT condition for our problem. Constraint is G1 to GM, and this is objective function. So if unconstrained case, we can ignore this part and this part, this part, this part. So only gradient, normal gradient is less than epsilon is enough as epsilon stationary point. But because of constraint case, we need to think of this KKT condition. And epsilon approximation was done. So epsilon is in here, here, here. And our approach is to reduce this left-hand side. So such direction is to reduce this quantity and moving in a feasible set, not to violate this condition, blah, blah, blah. This is a Lagrangian multiplier, so need to be non-negative or something like this. So we, if direction is small enough, and if the direction, if the solution, found solution satisfy this one, finish. So this is the algorithm we developed like this. So the such direction is computed like this. Now I forgot the definition of M, but M is something like random matrix, just scale random matrix. So now MK is the right random matrix and Lagrangian multiplier for this one. And we prepare two options for such direction D. If D, normal D is small enough and Lagrangian multipliers are non-negative, then finish. We could find the epsilon KKT point. Otherwise, change the calculation of DK such direction so as to increase the Lagrangian multiplier. So this is our algorithm. And so let's check the relationship to gradient projection method. Earlier, I mentioned that our algorithm is a random projection variant of gradient projection method. And then if we choose identity matrix for MK, then it's exactly the same with GP. And so it implies that our method is a kind of a random subspace variant of gradient projection method. And but our method need to move a little bit inside of the feasible region like this. So technically, it's not quite the same with this original method, even if we set MK equals identity. But yeah, we could not, yeah, we need to move inside a little bit. Oh, just, oh, yes, that's right, randomness. Yes, that's true. Okay. Yeah, I will skip the details, but the second option, yeah, search direction for the second option can increase the Lagrangian multiplier. Okay, and yeah, so to deal with non-linear constraint, we just calculate tangent space, tangent space, and gradient projection is done on a tangent space of physical set C if C is a non-linear physical set. Okay, so that's it. So let's move to theoretical results. So this is again KKT, epsilon KKT conditions, and assumption is not so strong and also, yeah, if we assume this one, we can get this quantity, and assumption B, it's super complicated, but if the previous assumption hold and GI are all convex, this naturally it holds. So yeah, ignore it if we assume constraint convex. Okay. So it's a theoretical guarantee. So epsilon KKT point can be found within this iteration. And the denominator is important because numerator is just a constant. So here it's shown like this. So complicated, but if n is large enough, k is something like this. And this iteration number of iteration to achieve epsilon KKT point. And yeah, so total complexity is something like this. So each iteration, order S computation is necessary, and it repeat at k iterations. So in total, this complexity. And on the other hand, if we set M identity without stochastic randomness, then this would be the complexity. So a little bit higher complexity than this one because of this S, a dependency of S. So this would be the price to pay to think of by thinking random subspace approach. Okay. But using this toy example, we confirm that our method can take a longer step size, as I mentioned. So this scale is -2, but here randomness, I use this subspace, then step size becomes larger. So it's a good point. And also we tested our algorithm using this deep learning. No deep, sorry, not deep, just a neural network and also convolution neural network. We tested our method using these examples. And we compare our method to original projective gradient descent, and also it's a state-of-the-art algorithm. And this one, yeah, identity, if MK is original space, just identity. It's very close to this one, but slightly different because our approach moves inside the feasible region. So yeah, our approach using random subspace is compared to these methods. Then this is numerical experiments. So for simple problem setting, not that different. So orange and green are our results, and B is 500, 100. Even though original problem size decision variable is like this, but with small dimension works well like this, and sometimes better. We won sometimes like this. So we use automatic differentiation for this case because it was possible to use it. But for convolutional neural network, it's out of memory. So we could not use automatic differentiation. We use finite differentiation for the gradient calculation. Then, yeah, then it's too large, too difficult for PGD or state-of-the-art algorithm. But in our case, we only reduce the decision variable size, so we could repeat the procedure like this and going down. So this green, pink color, and this one subspace method by changing the dimension. Oh yeah, machine. Yeah, sorry, this is the function evaluation. Function value, and this one function evaluation. Yeah, if we write here as a iteration number, maybe yes. Let me see. Wait, not same. Sorry. Like this. So iteration number is just kept this number, but each iteration different computation time. So we decided to plot using the time. Okay. So yeah, for this case, it works well. If a small number of dimension works, so we choose this one from this one randomly, but yeah, it works. So yeah, this is my talk, and we did this kind of work, and we got we found some confirmed advantage of random sample projection method. That's it. So thank you.
Any questions?
Could you take advantage of several random subspace?
Several random.
Yeah, more than one.
At the same time?
Yes, or sequentially, or some combination.
Okay, in a sense, we already did it. I forgot to mention it, but we update random subspace every iteration. So, for example, at kth iteration, we choose this random subspace to move. And if we reach to this point, change the random subspace at the k+1 iteration. So every iteration, we change the subspace. So did I answer to you?
In some ways.
Oh, okay. Yeah. Yes, that's right. Actually, yeah, thank you for nice comment. Yeah, actually, this is the next thing that we try to do. We forgot to compare to the just coordinate this method. So yeah, we would check later. But theoretically, no theoretical guarantee. Of course, we can decrease the number of sample size, like 5 or something, but 5 obviously not that good. So yeah, pink is 50. Sorry, D is S. Sorry, I changed the notation in the middle. I know. Yeah, sorry. Here only 50, 100. But if we decrease the subspace size too much, and then 5D equals 5, then the worse, the performance becomes worse. So of course, it depends on the application. But I think if we set D equals 1, no good performance. And if D equals 1, it's almost the same with coordinate descent method. But coordinate descent method means the coordinate-wise direction. But this one, coordinate is only one direction. So general version of coordinate descent method. Thank you.
Okay. I wonder, can you handle the case where the constraint of x is that each x can only be 0 or 1, but u can be continuous, because this is the case for binarized neural network that is very close to your motivation. The back propagation is not really possible, but the function evaluation is always possible.
Okay, so I don't know the problem setting very well, but X can be sparse. You mean that?
X can each X can only take a value 0 or 1, but U can be continuous. Then maybe I can if you can apply.
Okay, yeah.
Because in your experiments, the constraint is that the L2 norm of X is smaller than some value. I want to whether you can handle other type of constraint. X can only take some few value.
Possible. We can deal with handle another type of constraint. And also, if I answer to your question, we can maybe it's better to change the matrix. Random matrix, I use just a normal distribution, but 0, 1, 0, 1, 0, 1, minus 1 or something. There's various variation for random matrix, the generation of random matrix. If we use such a sparse random matrix, maybe we can keep the structure of the original problem like you mentioned. Sparse.
Okay, thank you very much.
Thank you.
Thank you.
All right, so I'm all that's standing between you and lunch. I also learned yesterday that today is a holiday, so I want to thank you all for being here on a holiday. So my research area is reinforcement learning, and I think many of you are not experts in RL, and so I thought about what I wanted to talk about today, and maybe one application that a lot of us have in common is training foundation models. So the stance that I want to take right now is that training foundation models for sequential data is really a reinforcement learning problem, right? So this is the current paradigm for training large language models and foundation models. The first stage is this pre-training using an autoregressive objective on a large unlabeled corpus. Usually this data can be very noisy or poor quality. And so then the next stage is to do fine-tuning for a particular task using something like RLHF. So using human preferences, learning a reward function from those preferences, and then using reinforcement learning, usually an on-policy method like PPO, in order to optimize for that reward function, right? So if we think about this from a reinforcement learning perspective, the first stage is really just doing behavior cloning. We're just training a policy to imitate the behavior policy that generated this internet data. And then, the second stage, fine-tuning, is actually using RL. So there's no reason that this has to be two separate stages, right? So ideally, we should unify this all from this reinforcement learning perspective and try to come up with a single pre-training objective for this unlabeled data so that we can learn an optimal policy for any downstream task and get zero-shot optimality for that task. So first, let's consider why behavior cloning isn't enough, right? Why do we even need that second stage? Some upsides to behavior cloning is that it's supervised learning, which is a very stable objective, unlike RL, which often has bootstrapping or policy gradient and is very unstable, or has high variance gradients. The downsides of behavior cloning, obviously, is that it is only matching the behavior policy, so we can never do better than the data that we have on hand, and so it's only going to be as good as your data set.
What is behavior cloning?
Sorry, behavior cloning is just imitation learning, right? So that's what the autoregressive objective. Sorry, okay. Let me go back to this.
Learning is reinforcement learning already.
Imitation learning, you can think about it from a reinforcement learning perspective, because when we say RL is a problem setting, right? A sequential decision-making problem setting, and it's a class of algorithms. So imitation learning falls under the RL problem setting. It's a way of solving a sequential decision-making problem, but assuming only that you have expert data and you're just trying to imitate that expert. And I'm saying we should actually be using reinforcement learning algorithms to do better than the data that we have access to, right? And so maybe I should also, when we think about this like foundation model problem, whether it's video generation or language generation, like how is this an MVP? How is this an RL problem? So your foundation model, your generative model, is a policy, right? And so it's just outputting tokens. So you can think of the space of all tokens as your action space. It's a very large action space. And then very trivially, the entire sequence that you've generated so far, including your context, you can think of that as your state. Right? So then when you generate another token and add that to your sequence, that becomes your new state. So this is how, this is an RL problem. Okay. So we want to come up with better self-supervised reinforcement learning algorithms to solve this problem of training foundation models, right? So we need to come up with self-supervised reinforcement learning methods, because in RL, the standard assumption is that you have access to a reward function. That's your learning signal, and you're just trying to maximize that reward. And with RLHF, you know, it's very expensive, but we're getting that reward from human preferences. And if we want to kind of change how we do the pre-training procedure, we need to figure out where is that reward signal going to come from. So instead of looking at reward, I'm going to focus on a slightly different formulation for the RL problem, which is occupancy matching. So instead of assuming that we have a reward signal that we're maximizing, we're going to instead assume that the problem, the reward, is given to us as a target distribution. And we're just trying to learn a policy that will match, whose occupancy, whose state visitation distribution will match that target distribution. And so we're going to look at this for like a simpler goal condition problem setting, and then extend this to figuring out ways in which we can like learn a basis for any downstream task. So one way to think about this self-supervised or multitask problem is through contextual MDPs, right? So the assumption is that you have all these similar tasks with different reward functions, but probably the same dynamics, potentially different dynamics. And all of that information about what makes these different tasks different can be described by a context. Right? So, and the question that we're trying to answer is, how can we leverage shared structure across these tasks? So to formalize this a bit, we would extend the standard Markov precision process definition, which assumes that we have some state space, action space, stationary reward function, stationary dynamics, transition function, with this additional context space C, right? And so C now can act on this reward and potentially transition dynamics, but we're not really going to cover that side. So the simplest context-based setting that we can consider is the goal condition one, right? So goal conditioning, I'm going to convince you of this, is a form of self-supervised learning. I'm going to show that this actually has connections to temporal contrastive objectives in more standard self-supervised learning. And kind of like a trait that we want from our methods is that we want to be able to perform this on large amounts of offline data. So in the goal-conditioned RL setting, the agent is being trained to solve a number of tasks within the same environment. Right? The goal is sampled at the beginning of the episode. This goal is just sampled from the state space. And our reward function is naturally given by just this sparse reward where the agent only receives a reward of 1 when it reaches the goal. So when we want to apply this in the offline setting, so the of this objective should look hopefully pretty familiar to some of you who work in RL, right? We're just trying to maximize the expectation of our discounted return within our episode, right? Where the reward is just that sparse reward given on the previous slide. When we work in the offline setting, we need to add a regularization term to make sure that we stay within our data distribution. Right? Otherwise, we can extrapolate wildly and learn policies that think that as long as we go outside of our data support, then we will achieve high reward, which is not necessarily true, right? So in the offline RL setting, we have to add this KL term to make sure that the state visitation distribution of our policy stays close to our data set. So it turns out that if we look at the dual formulation of this objective, we get the very messy expression on the bottom. The nice thing about this dual formulation is that it's actually very easy to optimize for this using our offline data set, right? So all we need access to is a probability distribution of our goal, our initial state, and transitions within a trajectory. And so when we look at this now, it should be pretty clear that this looks a lot like a temporal contrastive objective, right? So if we take this dual formulation, and let's just assume that V star is something that's known. So now we can take away the minimization over V and bring in the first term, combine these two terms. Now this is starting to look a lot like an info NCE objective, right? So our goal is really our anchor, right? And then we have, this is maybe a little bit counterintuitive, but our initial state and our goal is considered a positive pair. And then temporal neighbors in this trajectory are considered negative pairs, right? And so this bottom term isn't actually performing an explicit repulsion in the same way that the info NCE objective is. It's really just minimizing this one-step TD error. So it's really implicit, but you can think of it as just, as the negative pair is just making sure that neighboring states are always a fixed distance of 1 apart, some unit distance. Right? So we want to make sure that all of these constraints hold true. We want neighboring states to be a distance of 1 apart while making sure that we're still attracting kind of like far away states or initial states and end states of each trajectory. Okay. So offline goal conditioned RL is implicitly time contrastive, and this leads to this long range, temporally smooth representation, this goal conditioned RL objective. So we're not the first to come up with this, this comparison between goal condition RL and contrastive objectives. So Ben Eisenbach had a paper at NeurIPS 2022 on contrastive learning as goal condition RL, where he also comes up with a contrastive objective for solving goal condition RL problems. All right, so that's just to show this connection exists, right? Another problem with solving this goal condition RL problem, this problem is hard, is that it's sparse reward. And so in RL, it's very hard to make any progress on the problem if you've never seen any learning signal yet, any reward, right? And so in goal condition RL, this is especially hard because reward is sparse. So if we, again, think about this from an occupancy matching perspective, it turns out that we have another source of learning signal other than the reward, right? We can use the F divergence between these distributions, our current state visitation distribution as given by our current policy, and our target distribution denoted by a goal, so just a Dirac at the goal state. And so there's all of these different F divergences that we could use as learning signal in this case. So then that gives rise to this new objective, which is different from the standard RL objective of maximizing reward, right? So we just want to minimize this F divergence between the visitation distribution of our policy and this goal distribution. And the intuition for this is that we want the agent to be at the goal state with high probability, right? So we want P theta S to be high at goal states and low at any other state. And so we just want to match these distributions as closely as possible, subject to the constraint that this occupancy distribution has to be legal, has to be allowed under the dynamics of our environment. So the first question that we need to ask is, does this objective actually produce an optimal policy, right? Does this objective converge to the same solution that maximizing our sparse reward would? Turns out the answer is yes. So how do we actually optimize this objective? It turns out that we can just minimize the F divergence by taking the gradient. So we derive the analytical gradient for the F divergence. And it turns out this actually looks a lot like policy gradient, which is just gradient descent on the original reward signal, right? So the first term looks a lot like policy gradient, where we're just kind of maximizing log probability of the policy. So in policy gradient, though, this term should actually be the reward, but we've replaced reward instead with this dense weight. And so this is, so this dense weight is now just important sampling ratio with the visitation distribution of our policy on top and the goal distribution on the bottom. And so one thing to note is that this is not a reward. This is not a dense reward replacing our sparse reward. This is a non-stationary signal because it depends on our current policy. F is the F divergence. F prime is the dual of whatever F divergence that we're using. So I don't think I actually have it, but yeah, so we actually have results for this for various F divergences, and so then you would just use the F prime for depending on which divergence you use. Yeah. Sorry, yes, PG is the target distribution, which is a Dirac at the goal. Yes, so in order to make this tractable, we actually incorporate an epsilon everywhere that's not the goal. Okay. So this actually looks a lot like maxent RL. So maxent RL is a variation on the standard RL paradigm where we aren't just trying to maximize our reward, but we're also trying to maximize the entropy of our policy. One way of thinking about this is that there can be infinitely many optimal policies for a task, but there's going to be only a single unique policy that is maximum entropy. And when we talk about entropy here, we mean the entropy over the action distribution output by the policy. So another reason why we care about maxent RL is because the idea is that if your action distribution that your policy is outputting is high entropy, then this will enable exploration, which makes it easier to find the optimal policy, right? And so the FKL, the forward KL policy gradient objective from occupancy matching looks very similar, but slightly different, right? Because instead of maximizing the entropy of the policy, we're instead maximizing the entropy of the state occupancy. And so it turns out that, so we're gonna rename standard maxent RL to policy maxent, and then our method we call state maxent. So it turns out that state maxent is actually a much more desirable trait to have in a policy compared to the standard policy maxent, right? So in this just simple grid world, the first two examples that we have are based on our method with different F divergences. And then the one on the right is the standard policy-based maxent. So you can see that when the policy, when the agent hasn't yet discovered the reward, which is just the red dot, so it has to go around this wall in order to find it, it's just a uniform distribution over actions, right? So it's just kind of just exploring its local space. Whereas the state maxent method will, when it hasn't received any reward signal yet, when it hasn't seen the goal, it's going to try to produce a uniform distribution over state occupancy. So it's actually going to very efficiently perform state coverage over the entire environment until it finds the goal, and then it uses that reward signal to try to maximize its occupancy at the goal. Okay. So it turns out that this can also scale up to more complex domains, larger mazes, as well as simulation robotics experiments. So the problem with this method is that because of this connection to policy gradient and gradient descent, it means that this is an on-policy objective. And so, one of the goals that we had in this talk is that we wanted a method, a self-supervised RL method that would work for offline data. So how can we actually scale this to offline data? So if we continue to look at this goal condition RL problem framed as occupancy matching, it turns out that occupancy matching is actually a lower bound for the maxent goal reaching problem. And so this result was originally in a paper by Jason Ma in 2022, and then also a variation of it is also in one of our papers that's going to be presented at ICRA this year. So an issue with this state occupancy matching perspective is that estimating this joint policy visitation probability is difficult. This is very difficult. So if we look at the dual formulation again, it turns out that this now allows us to perform offline learning, right? So let's come back to the distribution matching objective, just the primal form. This now looks a little bit different from the version that you saw previously. So this constraint is just called the Bellman flow constraint. And so as we've mentioned already, this is just making sure that the visitation distribution is actually valid under the dynamics of our environment. And then we're actually now, instead of just using the state visitation distribution and our target distribution and computing the KL between those, as established, it can be the case that they have no shared support. So instead, we're going to use a mixture distribution. So we're assuming that we have this offline data. So this offline data visitation now we denote by rho. And we can now set our objective to minimize the F divergence between the mixture of our current policy visitation and the offline data visitation, and a mixture of the target distribution and that offline data visitation, right? So now we can avoid kind of having a zero at the bottom of in the denominator, right? All right, so we can compute the dual form of this objective, and it turns out the primal and dual share the same optimal solution. So we can just directly optimize for this dual form. So if we look at this dual form, the first two terms are just trying to decrease the score of our value function under the current policy, our current policy, right? Or sorry, decrease the score at transitions under our current policy. The next term is now trying to increase the score of transitions at our goal, or whatever our target distribution is. And then the final term is just this smoothness, this Bellman regularization, making sure everything is valid. So this is our method, mixture occupancy matching with the dual objective. And so again, it should be pretty obvious that this objective has this contrastive flavor, right, of just pushing down the score of transitions under our current policy and pushing things up under the target. And so it turns out that this occupancy matching based approach leads to very good results in a lot of the offline RL benchmark environments that we use. These are all kind of like simulated robotics experiments. GoFar is another occupancy matching based method because it also derives a dual objective for the goal conditioned RL. But it is based on a coverage assumption and requires the use of a discriminator, which our method does not. And then we also have a comparison to behavior cloning based methods. This goal conditioned supervised learning is just standard behavior cloning, which means that our performance is very tied to the quality of our data set. And then this weighted goal conditioned supervised learning uses a weight term based on the value of the transition. So we expect to see a little bit better performance there. And then this contrastive RL is using a contrastive based approach, that was from Eisenbach's paper. And then these are just methods using the standard RL formulation and sparse reward. Okay. And then we find that we can actually scale this up to high dimensional tasks, so image-based experiments as well, where we achieve better performance compared to prior methods that are based on RL, the standard RL paradigm. So it also turns out, because we're using this mixture distribution in our objective, that we're actually pretty robust to decreasing data coverage. So here in this experiment, we just reduce the amount of expert data that we have access to in our offline data set. And we find that our method still scales pretty gracefully with this decrease. So the downsides of goal conditioned RL are that not actually all downstream tasks are goal conditioned. Right? So if we think about what we actually want when we train foundation models, it's not that we want to have some goal token at the end of our sequence, right? The context, the indication of what our task is often much more complex than that. So how can we actually construct a self-supervised objective with guarantees of generalizing to any downstream task, not just ones that are described by a single goal state? So effectively, RL is the observation that we're using is that RL is essentially a linear program, right? Let's see. The Bellman equations are affine, right? So this is just the kind of like bootstrapping objective for learning the state visitation for a policy. And given that we know these Bellman equations are affine, an interesting question comes up, which is, can we learn the basis of the solution space, right? So any particular solution will just be a linear combination of these basis vectors. And you can think of these basis vectors as just representing a compact representation for the Markov process. So a generalization of the state visitation distribution that will be useful for us is the successor measure, right? So the successor measure is just defined as the probability of being in state S plus and taking action A plus under some policy when we started from state action SA, right? And then this computing this successor measure also follows a similar Bellman equation as the original state visitation distributions. And we can now represent, we want to learn the basis vectors for this successor measure, right? So we know that we can represent the successor measure for any policy in this linear form. And so now we just want to learn phi and b. And for any given reward function, we just need to solve a linear program on W. So how does this actually relate? How do visitation distributions and successor measures actually relate to Q functions? So given a task reward function R, you can rewrite your standard RL objective as just your visitation times your reward. Right? And that should be pretty clear that multiplying those two things together automatically gives us the value function, which is the discounted return. And so then you can also write the Q function with respect to the successor measure as just m pi r. Okay. So the benefits of this is that it allows us to perform simple inference on any reward function. We get zero-shot optimality as long as we can find this W. We can use this to extend FPG to learn better representations of state visitation and also now generalize this to the offline setting. And this objective is ideal for environments where the reward is not known, right? Which is the standard foundation model setting, where we just have access to a large corpus of unlabeled data. So in order to learn phi and b, this is our loss objective, right? So we've just taken the standard Bellman update, and instead of the Q function parameterized by some neural network or something, we've just replaced it with this linear expression, right? Phi w plus b. And we just have, yeah, so we're just plugging that into the standard Bellman update. And now comes the hard part, which is that we're saying that we want to minimize this for all possible policies. In order to do so, we need to solve this bi-level optimization problem, right? If we can do this, then we can perform fast optimal policy inference on downstream tasks, right? So if we take this back to the original application, right? If we were to use this for LLMs, what we're saying is we can train an optimal policy for any possible visitation distribution, any target distribution over tokens using just that unlabeled internet data corpus, right? So, and we know that for any downstream task as denoted by this reward R, our optimal Q function just corresponds to solving this objective for W. Right. So we can't just maximize this objective because W has to is subject to the Bellman flow constraints, right? The corresponding successor measure has to be valid. So we have two approaches for this constrained problem. One is to just use standard RL, where we're just performing Q iteration to optimize for W star. And then the hope is that we're doing this in a much simpler space, right? So this should be much more sample efficient than trying to do reinforcement learning from scratch or reinforcement learning fine tuning from the behavior policy extracted from that stage 1 pre-training. Or we can just solve a constrained linear program, which we can do when the problem space is smaller. All right, so just to summarize, I've shown that self-supervised RL has connections to contrastive objectives. I think that there's a lot more that we can do in this space. I think that this means that maybe we should be trying to train generative models using a contrastive style objective rather than autoregressive. I think that we should view training sequential generative models from an RL perspective. And so this is I think like a very good reason to explore self-supervised RL more. And then I presented 2 approaches to self-supervision based on occupancy matching and basis set learning. Thank you very much.
Any questions, comments?
Thanks. So I'm not an expert or reinforcement. So maybe my question is stupid, but so you are minimizing the visitation distribution and goal distributions.
The F divergence between those 2 distributions, yes.
But is it appropriate? So maybe we should minimize the distribution distance between the stationary distribution and the goal distribution.
What do you?
Stationary distribution means that so you take it a t to infinity, so then you have a kind of a limited distribution.
So this is the visitation distribution for the policy that we mean. Is when you run your policy. Sorry, I should have defined this. When we talk about a state visitation distribution for a policy, we mean when you run that policy into infinity and you have a steady state distribution for that policy. So that's the distribution that we're trying to move as closely as possible to your target distribution.
Okay. Sorry. So I thought the visitation distribution is the distribution of accumulating across that time. No, not that t to infinity, but just a kind of summation.
Oh, I see. Oh, I see. I see. Actually, yes. No, you're right. You're right. You're right. It's a discounted. So yeah. That's why we talk about the successor measure as opposed to visitation distribution. You're right. Sorry. It is like a kind of like a discounted visitation distribution, which means that we care more about the occupancy early in your policy rather than later in your policy. And the reason for that is because it's to match the fact that in RL, we're usually trying to maximize for discounted return, which means that we care more about achieving higher reward as soon as possible rather than over infinity.
I see. That makes sense. Yeah. Thank you.
Thank you for your talk. Have you tried to apply your idea with bandits, not reinforcement learning?
Try to apply.
Multi-armed bandits is a type of stateless reinforcement learning.
I'm not very familiar with if this approach has been looked at with bandits. But it would make sense. I think it would be very simple if you knew what your target was in the bandit problem, because then you would just always, that automatically gives you your policy, right? Because you just want to pull arms with that same target distribution. In the RL problem, it's much harder because the dynamics of the system are unknown. And so how to match that target distribution is a much harder problem with a long time horizon in a sequential setting.
But the suitable bandit type is important.
So maybe one thing to point out is that the reward paradigm and this target distribution paradigm are operating on slightly different assumptions. It can be difficult to get access to a target distribution for a lot of tasks, whereas it can be very easy to define a reward. And so that's kind of a trade-off that I didn't really mention.
Thank you.
Okay, thank you very much for the last part. So I also think that optimizing fine B for all the policies is quite challenging. Yeah. So can you narrow down the policies based on the offline data samples.
Yes.
And also the practically, so the grid world or robot control task, what's the number of number of the base functions you would need for the application?
That's a good question. I suspect the number of basis vectors that we need is maybe more of an empirical question. For your first question, we already are constraining ourselves only within the data distribution, considering tasks within our data distribution, because we are looking at the dual of the offline RL objective in the primal form, which has like the KL term that makes sure that we stay within the data support. This is still a very hard problem, especially if you're considering like a very, very broad, very complete offline data set. And so then another possibility is can we use some set of example tasks that we believe form the basis for every downstream task that we may care about? And I think that would be an easier way to do this. So we have some preliminary results in simple environments showing that we can just optimize for this objective directly. But I agree with you. I think that if we try to scale this up, we may start running into computational issues because this is just a very, very hard problem. And I think the solution to that would be consider a smaller space of tasks.